Hi, welcome back to my channel. My name is Gina. In this video, we are going to talk about a technique to solve an integral, the partial fractions. When do I use integration by partial fractions? First, the integral is not a basic formula, and the u substitution fails. If you want to review the basic antiderivative and u sub, I'll put the videos in the top right corner. And the third hint to use partial fractions is when you have an integral where the integrand is a rational function with two or more factors at the denominator. Here are some examples. Integral of 2x plus 1 over x times x minus 2 times x plus 1. And in the second example, we have 2x plus 5 over x cubed times x squared plus 1. There are three cases for the partial fraction decomposition. The first one, if you have distinct linear factor, and that is the case for the first example. All the factors in the first example, the x minus 2, and x plus 1, they are all distinct linear factors. In the second case, you can have repeated linear factor. That is the x cubed in the second example. And the third case is when you have quadratic non-reducible factor. For example, the x squared plus 1 in the second example. So how do you use the partial fraction decomposition? When you have distinct linear factor, say you have numerator as a function of x and denominator as a function of x, where the denominator is a combination of two or more linear factors. Then you can rewrite this as a constant over the first linear factor plus another constant over the second linear factor plus a constant over the third linear factor. And for the second case, when you have repeated linear factor, for example, you have numerator as a function of x, and denominator is part of x to the power of k times some other factors. Then you can decompose this as a constant over the repeated linear factor out of x plus another constant over the linear factor square plus a constant over the linear factor cube until when you get k over the linear factor out of x to the power of k, and other terms for the other factors. And for the third case, when you have quadratic and its non-reducible factor, then its decomposed form requires a constant times x plus another constant over the non-reducible quadratic factor. Let's look at this example. Here we don't want to solve the integral, but we just want to decompose the rational function. So here in the denominator we have x plus 1 times x cubed times x minus 1 squared times x squared plus 2x plus 2. For the first term, the x plus 1 is a linear factor. And x cubed and x minus 1 squared, they are repeated linear factors. And the last factor, x squared plus 2x plus 2, it's a quadratic factor and is non-reducible. So using the partial fraction decomposition, we can rewrite this rational function as a constant over the first linear factor, x plus 1, plus a constant over x plus a constant over x squared plus a constant over x cubed. So this is for the linear factor, and this 3 is for the repeated linear x cubed, and plus a constant over x minus 1 plus a constant over x minus 1 squared. So these two terms are for the repeated linear factor x minus 1 squared. And then for the quadratic factor, we can decompose that as a constant times x plus another constant over the quadratic factor x squared plus 2x plus 2. And this is for the quadratic factor. Now let's solve this integral using the partial fraction. Here we have integral of 2x squared plus 1 over x plus 1 times x squared plus 1. So in the denominator we have a linear factor, x plus 1, and the x squared plus 1 is a quadratic factor. So using the partial fraction decomposition, we can rewrite 2x squared plus 1 over x plus 1 times x squared plus 1 as a constant over the linear factor x plus 1 plus a constant times x plus c over the quadratic factor x squared plus 1. Now let's multiply on both sides by x plus 1 times x squared plus 1. The left-hand side equals to 2x squared plus 1, and the right-hand side equals to a times x squared plus 1 plus bx plus c times x plus 1. Now let's expand the right-hand side. Ax squared plus a plus bx squared plus bx plus cx plus c. Now we can compare the powers on both sides. We can compare x squared, x, and constant. For x squared, the left-hand side we have 2. On the right-hand side, we have ax squared plus bx squared. So the right-hand side for the x squared, we have a plus b. And for x, on the left-hand side, we don't have any x term. So the left-hand side is 0. And the right-hand side, we have bx plus cx. So the right-hand side is b plus c. And for the constant, on the left-hand side, we have 1. And the right-hand side, we have a plus c. From the second equation, we get that b is negative c. And we substitute this in the first equation. 2 equals to a minus c. Now let's add this equation with this equation. equation 1 plus equation 2, we'll get 3 equals to 2a. So a is 3 over 2. And let's substitute this back to equation 1. We get 2 equals to 3 over 2 minus c. So c is 3 over 2 minus 2, which is negative 1 over 2. And from here, we know that b is negative c. So b is 1 over 2. So the integral we want to solve, 2x squared plus 1 over x plus 1 times x squared plus 1 equals to integral of a, 3 over 2, over the linear factor x plus 1 plus bx plus c, that is 1 over 2 times x minus 1 over 2, over the quadratic factor x squared plus 1, which equals to 3 over 2 times integral of 1 over x plus 1 plus 1 over 2 times integral of x over x squared plus 1 minus 1 over 2 times integral of 1 over x squared plus 1. For the first integral, we can let u be x plus 1. So du is just dx. And for the second integral, we can let u be x squared plus 1. So du is 2x dx. And for the third integral, it's a basic antiderivative. It equals to arctan of x. So this equals to 3 over 2 times line of absolute of u, that is x plus 1, plus 1 over 4 times line of absolute of u, x squared plus 1. And the third integral, minus 1 over 2 times arctan of x. And remember to add some constant at the end. And that's the end of the video. Thanks for watching. If you like my videos, please like and subscribe, and I'll see you in the next video.